So welcome back, guys. That is the most controversial opinion that I hold. So thank you for letting me share that with you. Today, we are going to start, and I'm going to do these next two sections like I wish I'd done the previous sections. If we looked at the two sections that were just parallelograms, the first section says, if it's a parallelogram, then we get these relationships. Do you remember any of them? What's true about if it's a parallelogram, what do I get for free? There's a whole bunch of stuff. Opposite sides are congruent. Opposite angles are congruent. What do the diagonals do to each other? They bisect, and any two consecutive or neighboring angles add up to what? 180. That's what makes, like, those are all, if it's a parallelogram, then this is true. And then the very next section, we went back and said, well, hold on here. If both pairs of opposite sides are congruent, then it's a parallelogram. And I probably whined about this when we were like doing it the first time. Did anybody remember what I said I wish I had done and what I will do next year with those two sections? I'm going to combine them because instead of writing this statement, if P then Q, and then later writing if Q then P, is there a more efficient way that we can use our time? If and only if, the double arrows. So today, when we're looking at our lesson, just so you guys are aware, we're kind of shoving two together because the same thing is going to happen. So this is really 6.5 and 6.6 kind of shoved together in that regard. I'll give you different problem sets. I just want to be able to write the theorems as their singular theorems here and now. Okay, so 6.5 is really what we're focusing on. And if you want to be real specific, we can say 6.5. And it's really, truly also 6.6 or parts of it. I care more that it's 6.5 though. Our entire focus in 6.5 is going to be on some special parallelograms. Now, you guys gave me the three that we're going to consider. And we're going to start off with what I don't know. There's no real particular order. Give me a shape and don't just shout it out. We're going to try the rock, paper, scissors thing. And we'll just see. Or do you guys want to learn a new way? Do we do the even odd game? Okay, so I'll show you a cool mathy variation of rock, paper, scissors as well. You're going to play one round of it. I want you guys, think about it for a second, to name a parallelogram with all four sides the same. What could I be talking about? Don't just shout it. Here's what I want you to do. On one hand, both you people, hide it from your other neighbors so under the desk. So I'm going to do a round with Sunny real quick. Sunny, put up any number 1 to 5 on one hand. Don't tell me the number. Like, do you have it up on one hand? Check it out. Now I just guess. Even. Hold up yours. What's 3 plus 1? And 4 is? I'm right. So I won that round there, or I'm the winner, quote unquote. Okay, with your neighbors. What's up? I just added them up, so check it out. I'm going to play with you 1 to 5, 0 to 5, okay? Hold up some number and guess even or odd. What do you think? Okay, hold up your numbers. 4 plus 1 is, which is not even, I win again. I'm undefeated right now. Okay, I want you, do we all know, like right off the bat, because I heard people talking, do you know the two parallelograms or the special parallelograms that I might be considering? So let me rephrase the question. What's the difference between a square and whatever the other one is? It's a rhombus. Chalk it out, figure out who's speaking. I'm going to go like 10-second explanation. Just figure out who's going to speak, who's going to listen. Is this yours? Like from, it's mine, I think, but it's yours now. I didn't set it on your desk. Okay. What's the difference?
Rhombus is like a diamond shape. They're like the same thing, just one's like if it was stuck and you pushed it.
How would you define a rhombus?
I would define a rhombus as a diamond. And that's how I define the rhombus actually, is that it looks like a diamond.
So why is that not just a parallelogram? What makes it a rhombus more than that? Okay. What do you guys think? What's the difference between those things, a rhombus and a square? I think that is something they have in common. And we'll see. Like, you're on the right track. I heard. Okay. All right, coming back together in 3, 2, 1. What's the difference between a square and a rhombus? What'd you come up with, Liam?
Square has 4 equal angles.
4 equal angles. 4 right angles. And what's true about all the sides of a square? They're congruent. What's a rhombus? So it has 4 sides. Let's see if we can't clean this up. So our first topic, we are going to define real quick for ourselves a rhombus. Now, the plural of which is rhombi, if you want to talk about multiple rhombus. Okay, as we're going through this, there is a single little tiny piece that will distinguish us between our rhombus and our square. And we're going to see if we can't find it just via the definition. A rhombus, and I'm going to underline one of these words. I want you to do the same. We're going to say that this is a parallelogram with 4 congruent sides. This is how we're going to define a rhombus. Now, 2 big, really important ideas that I want to get out here. The first of these, and this is the underline that I want you guys to add, is the fact that a rhombus is still a parallelogram. This is super duper important. We spend a lot of time on parallelograms because turns out some of these other really nice shapes are also parallelograms. If it is a parallelogram, do I know anything about it without thinking about rhombus specifically? What's true about the opposite sides? What's true about opposite angles? Consecutive angles. What do the diagonals do to each other? Bisect. So we're just going to make this little comment. I like to word it like this. Because it's a parallelogram, it inherits all those properties. And they're those properties that we just listed. The diagonals bisect one another, opposite sides congruent. Everything that we had before about parallelograms still applies. What I'm hoping is we can go a little bit further than that. So it inherits all of the properties of parallelograms, but then all of a sudden something else shows up. Why is this not a square? The angles. Now, with just this definition, is a square, bless you, a parallelogram? Does it have 4 congruent sides? So what do you think we can say a square is? It's a rhombus with 4 right angles. That's it. It's just a rhombus. It's just a special rhombus. Now, what I want to dig into is these, and maybe we get some more properties. So we're going to sketch as best I can a rhombus. We'll make sure it is a rhombus. And they kind of honestly just look like parallelograms. I will need your guys' a little bit of feedback. Do those lengths look about the same? Okay. Now, even if they don't look the same, is there a mark that I can put on my page to ensure that they are? Yeah, I'm going to put the dashes on it. So I'm going to name this thing RHOM for now. And then I'm going to add the diagonals. And where the diagonals intersect, we're going to say is point B. B is in Bravo. Okay. Now, here's what I want us to think about with these. I have a challenge for you guys first. Now, I want us to make some observations with these or about these shapes. And I'm going to give us a little guidance on how we're thinking about them. I already know what's true about the opposite sides. They're congruent. Why do I know they're congruent? It's a parallelogram. Yeah, 100%. I already know that this top side is congruent to this side and parallel simultaneously. Anything else that I know right off the bat? So we're going to switch this around. I'm going to give you guys 60 seconds. Talking with your neighbors, I want you to help me figure out what is everything that we know about this already, or if you see some other interesting observations that we might be able to make out of it. Without guidance, I hope maybe we'll see. 60 seconds, I'm going to call randomly on people so I don't just get blank silence. What marks do I get to put on this for free based on the fact of everything that we've said here? Okay, talk it out. I'm going to call on random people. What are you trying to assume? We put most of the marks for parallelogram stuff up there. Now, here's what I want you to do for me. I'm going to do some observations, and you're going to have to help me make these observations. So observe, and we're going to see if we can get a few things to happen. I want you guys to find me and justify the following. Finish this statement. Triangle, I'm just going to use HBO. So triangle HBO is congruent to, and I'm going to stop there. I'm going to give you guys a little bit of time. Here's HBO. What is that yellow shaded triangle guaranteed congruent to? Talk it out. So maybe you have an idea in your head already, and I think that based on what I heard, I think you have the right idea. I need you to justify it. This is going to be a quick one, like 30-ish seconds. What is this triangle congruent to is the question at hand, and we'll meet back 30 seconds. Talk it out. Gian, I love it. Yes. Oh, sorry. Okay, I'm going to call on one random person in 3, 2, 1. Number 8. Who dat? All right, Ronaldo, what is triangle HBO congruent to? Okay, MBR. Did anybody else have triangle MBR? Now, it's not the only choice, and here's what's cool about this. Some of you guys probably said MBR. Some of you might have said RHB or whatever order. Some of you might have said MBO. There's 4 triangles here. If we are looking at just this one, which is true, how do I know that's true? Side, side, side. And let's see, we went MBR. Do we agree that we have 3 sides marked on both those triangles? Okay, and let's see, is MBR the right order? It looks like it is. Now, what's true about, like, it doesn't matter which one we picked. I picked this one arbitrarily because it's the answer somebody gave me. You could have given me any of these and it would have been okay. What's true about the corresponding parts of these triangles? They're all congruent, right? So these ones work fine, and I'm just going to go ahead and shade a different one as well, and we're just going to see, like, these are the same. Is this one the same too, though? If we look at HBO, is that the same as MBO?
No, because the parallel.
Ooh. Maybe I have an unintentionally misleading mark. What did I mark here? Because a parallelogram, right? But we went a step further. I just haven't changed my mark yet. What sort of parallelogram is it that we're looking at? So not only are opposite sides congruent, what do I know about all 4 sides? So maybe it wasn't on purpose. How many dashes should this one have? If this has 2, this better have 2 as well, right? So we're going to add those back in. And now that we've done that, does it open the door for all those other triangles? Because now we have all 4 sides. If I, for example, were to shade this one. We do not need 2 arrows because the arrows indicate what's parallel to what. We can only have 2 pairs of sides be parallel because if they're all parallel, we just get 4 lines. Are yellow and green congruent? Now, here's the bigger part that I want us to think about. These are congruent as well by side, side, side. Now, really, all 4 of these triangles wind up being congruent, and that's pretty important in the end. And I'm just going to make a note here, all 4 triangles, and we'll just have a little follow-up underneath. Because it's not just those, it's all 4 of the triangles that get made. And we could side, side, side our way through all 4 of them. Now, the fact that if I were to look at just these 2, green and yellow, or just these 2, orange and green, it doesn't really matter. Do these angles match up, you think? And I'm looking at these 2. And I'll even label them here, and just so we can talk about them. And there's going to be a bunch of numbers if we do all of them. I'm going to look at those 2. Do those 2 angles, 1 and 2, correspond? HBO and MBO, they have to. What do 1 and 2 have to add up to together? Why? It's a linear pair. They form a straight line. And if these 2 are the same and they have to add up to 180, what are all 4 of these angles formed by those? So check it out. From just these triangle similarities, we get a huge implication. All 4 angles formed by the what? I would take bisector, but there's a different one. What's the line that connects R and O? Diagonals. Good. All 4 angles formed by diagonals are 90 degrees, which means right off the bat, we get a ton of option for which wonderful theorem to use when solving. If all of these are 90 degrees, it means every triangle here is a right triangle. Who? You could use hypotenuse leg, but there's an older idea. Greek-sounding name. The Pythagorean theorem will certainly apply to these. Okay, beyond that, I'm going to label two more. I'm going to put angle OHB. I'm going to call this angle 3. Where should I put angle 4, the angle that is congruent to, guaranteed? If that's 3, what's it the same as? Over here? What if I argue here? I'm going to make a claim. I think these are congruent. I want you to tell me the why. We'll do that same like 30 seconds. Why are 3 and 4 here congruent, even though we're not using the alternate interiors? Voila! It's fun because I get to see what failed with third hour in very different dynamics regardless. But like, it's the same stuff. I'm changing it a little bit based off the awkward answers that we got fourth hour, which is super nice. What do you guys think? Sorry to hear about your tummy. Why do you think 3 and 4 are the same?
Because they're congruent.
If we could fold it over, it would have to be the same, right? Okay. Pardon. Okay, the question at hand is why were these congruent, 3 and 4? And I'm going to put some asterisks here to make my observations. Angle 3 is congruent to angle 4 because, and I'm going to use these dots here, those 3 dots formed in the downward looking triangle, it's because. Why are they the same? We can't use alternate interiors. They're corresponding. If we were to fold this directly over, 3 and 4 line up, right? Or corresponding parts of congruent triangles are congruent. Now, because corresponding, I'm just going to say CP, CTC. Corresponding parts of congruent triangles are congruent. But we're going to shift focus. I'm going to add one more angle. I'm going to add angle 5 right there. BMR. Base metabolic rate. I think that's kind of out the window as far as science goes for anybody who's physical based. Are 4 and 5 the same? Because these triangles are side, 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 and so are these two, right? Like all 4 triangles we've already decided are the same. If I were to fold this over, would 4 and 5 line up on themselves? So not only do I know that 3 and 4 are the same, which is kind of unique because they're on the same side, but I think that angle 4 is congruent to angle 5 as well. Now, here's the big part that I want to see why we're talking so much about this. If I cut out just one little part, and I'm only going to cut out a small section, I'm going to do ROM, just this little tiny piece of my whole rhombus. RO and M. This is part of my diagonal, right? Up to B. Have I lost you guys so far? All I've done is taken out green and orange, and I just put it down here. Well, what's true about these 2 angles that we just discovered? So what did that diagonal do to this angle down here? It bisected it, and it was perpendicular. It was the perpendicular bisector of the segments, but it was also the angle bisector, I think. Oh, my theorems coming out of this. Today in class, we're going to be, I know we only have like 5 minutes left. I'm going to break your hearts real quick. There's no homework tonight. Well, hold on. I could be convinced. Okay, here we go. We are going to leave ourselves at a nice spot here. In dealing with rhombus, what we're going to use and get today is 2 theorems. Now, it's really 4 because I'm combining the 2 sections. We're only going to write it as 2 theorems. So here we go. We'll say that within our rhombi or rhombus section, we're going to get some nice theorems. And these don't get like their own names. We'll just say theorems for rhombi. Okay, 2 wonderful new theorems, and I'll just switch colors here. Our first one in blue is theorem 6.16, and then I'm going to put it in brackets as well because I think it's also 620. There's 2 theorems that we're writing here because we're going to write the original and its converse. Now, we already know that the diagonals of a parallelogram bisect one another? At what angle did they bisect one another? You say it again. 90. What do you call the segment that cut something in half at a perpendicular? There's an adjective I need in front of bisector. Perpendicular, right? So check it out. For a rhombus, we have the following. If it's a rhombus, then the diagonals perpendicularly bisect one another. What do you think 6.20 says? If the diagonals bisect one another perpendicularly, then it's a rhombus. It's just both directions. So we're going to write this as a single theorem. A rhombus or a parallelogram is a rhombus. And here's our theorem. A parallelogram is a rhombus. And I'm going to write 3 words here. I'm going to write if and only if. Just kidding, that's 4 words. Is there one single word that you could write in place of if and only if? If, with 2 F's. A parallelogram is a rhombus if and only if the diagonals perpendicularly bisect one another. Now, I try not to just keep speaking as you guys are writing this. A parallelogram is a rhombus if and only if the diagonals perpendicularly bisect one another. We just did a bunch of the logic to try to see this. What did we really do without ever saying it? We were really just logicking out the proofs for these things. We just weren't doing it formally. We're saying, here's the logic, deductively it leads to this, and we're done. We just didn't formally prove it. Okay, there's one more theorem that we got out of this. How do I say this part, that 5 and 4 would be the same, or that those would be the same, or that these would be the same, or these would be the same? How do I, and maybe I should use these. How would I word out that theorem, this second observation we made? Love it. Each diagonal bisects the angles, the interior angles of that foregone. So we're going to get one more theorem, and this is the last thing that we're going to write, and I think I might have a vocab word for you today. Theorem 617, and what other theorem might this be? 21. It's the theorem and the converse. So here we go. This time we're talking about the diagonals and the interior angles. A parallelogram is a rhombus. And I'm going to write the singular if here for if and only if. What do the diagonals do to each interior angle? Each diagonal bisects interior angles. Now, a parallelogram is a rhombus if and only if the diagonals bisect all the interior angles. Now, in either of these situations, we have the first that says, here's how we check if something is a rhombus, or if it is a rhombus, here's what we get, and here's the how do we check if it's a rhombus or not, just like we saw with parallelograms. Now, in these problems, we're going to start tomorrow right off the bat doing some problems regarding these theorems. We can get real proofy if you want. We can get less proofy if you want. Last little question. If I said this statement, I punked them, do you know what I mean? Not beat up. Reasonable. I've tricked them. I have tricked them. To punk is to trick. Cool. There's a show in the early 2000s called Punked with Ashton Kutcher, and all he did was trick people. All right. If you don't like your quiz score, fix it by when? Bet. All right, later, Raiders.